In this lesson, we're going to talk about chemistry as it applies to microbiology. Anytime we start to talk about chemistry, it is elements that we're really referring to. And a periodic table of elements, like you see right here, shows us all of the elements that are known, and we can get some general features and properties of those elements just by looking at the table and knowing what the numbers that we see on here mean and represent. Now, there are a lot of different elements, but the four that we are going to be focusing on specifically is going to be hydrogen, and then carbon, nitrogen, and oxygen over here. And the reason that we're focusing on those four is because they do make up together 96% of living matter. And so if it's 96% of living matter, that means that these are going to compose 96% of microbes, which again is really what we're focusing on in this course. Now, the atom is going to be the smallest unit of matter that still retains the properties of an element. So if we had an atom, we would be able to look at the properties of that and determine whether it was an atom of carbon or whether it was an atom of nitrogen or phosphorus or sulfur or some other particular element. So that's what we mean by it being the smallest thing that still retains the properties of that particular element. Now, there are smaller pieces of the atom for sure, and those smaller pieces are called protons, neutrons, and electrons. If we talk more about these subatomic particles, each one of them has a specific charge associated with it. So if we go over those charges, the protons are going to have a positive charge, or specifically +1 each. The neutrons are going to be neutral, so we're going to call them 0, and the electrons are going to have a negative charge, or they're going to be -1 each. And each one of these, besides having a specific charge to it, it has a specific place that it happens to be located at in the overall scheme of the atom. We will have certain particles that are located right in the middle, so we're going to call that middle section the nucleus. I'm going to draw that right here, so I'm just going to put a few particles right here, and these particular ones I'm going to put a plus on because those are going to represent my protons. I'm going to have some other particles that don't have anything on them, and I'm going to put 2 of those, and that's because those are going to represent my neutrons, which happen to be neutral. That right there is what we call the nucleus. Okay, so this is the nucleus. The nucleus is going to contain these 2 right here. So these are found in the nucleus. If we have stuff that's positively charged and we have neutral things in the nucleus, then overall the nucleus is going to have a positive charge to it. That is where you find the bulk of the atom with regards to mass. So in other words, that's kind of the heavy part of the atom if there was anything that was heavy. And then the electrons, they are going to be around the outside, and I'm just drawing it kind of like that because they happen to be moving all of the time. And so here I've got, I'll put 3 electrons on here. They are moving all of the time. The actual kind of path of their movement is going to vary a little bit, but we think of them as kind of just moving around in constant motion. The way that we draw that or represent it on a diagram like this is a little bit different depending on how involved we need to get into the discussion of that. So for our purposes, we're going to show it as just a plain circular path, but that's not always going to be a real true representation of what they're actually doing. So just to sum up what we've got here, atoms are going to have 3 smaller pieces to them. They will have 2 of those, the protons and the neutrons, located in the nucleus. So that's the very center. And then those electrons are going to be just spinning around the outside in constant motion. So a positive center, a negative area on the outside. Now, if we talk about what makes one atom different from another atom, or what makes one element's atoms different from another element's atoms, this is really where the atomic number comes in. The atomic number is the number of protons that a specific element's atoms contain. And so it is going to be unique to a particular element. That means that no 2 elements actually have the same atomic number. And so if you look at the periodic table, we can see how the numbers at the top of the boxes just increase as we go across those rows. They go up by 1. And so we can see right away looking at the periodic table that none of the boxes have the same number in the top. And again, that is the atomic number. So if we look at just some of the ones that we're going to be focusing on, notice here that carbon atoms will always have 6 protons. And the reason for that is because we can see a number 6 in the top of the box. So carbon will always have 6 protons. If we have an atom that has 8 protons, well, that would be something else. And we can see right here, if it's an atom that has 8 protons, that's going to be oxygen, because oxygen has the 8 in the top of the box. So that's the usefulness of the atomic number. Now, if we look at an atom, we can see that the number of protons is not going to vary. It's very characteristic for a particular element. But what can vary is the number of neutrons that are there. And when we do have different numbers of neutrons, we refer to those as isotopes. Isotopes are going to be just different atomic forms of an element, so different atoms that actually represent the same element, but they do have that different number of neutrons. And if we look at these 3 examples here on this slide, these are 3 examples of lithium, which is a smaller element. The atomic number for this one is being written right here as a subscript. So lithium always has 3 protons. That's what that number is showing us. And we can see in these 3 pictures that every one of those lithiums has 3 protons. And that would always be the case because 3 is the atomic number of lithium. However, if you look at the top number there, the superscript number, each one of them has a different number in that location. And that's because they do have a different number of neutrons, which we can see as the brown particles. So the first one has 3 neutrons. The second one has 4, and the third one happens to have 5 neutrons in it. And the reason why we're seeing that larger number increase on the top is because this number right here happens to be the number of neutrons plus the number of protons. So it's really telling us how many particles we have in the nucleus of that particular atom. It is also an estimate of the mass of that atom, and that is because protons and neutrons both weigh 1 Dalton each. Dalton is a unit of mass. It's an extremely small unit of mass, and so when we see the 8 there, we know that that atom has a mass of approximately 8 Daltons. We also refer to that number as the mass number. So the mass number is an approximate mass. It would be written as a superscript right here in front of the element symbol. Now we've talked a little bit about the nucleus of the atom, and that's because the nucleus is going to determine the atom's identity. So it's going to tell us what element we're actually looking at, tell us a little bit more about that element as far as what its mass actually is. But the electrons, the parts on the outside, they are what ultimately determines the chemical behavior of the atom. And if you just think about it, if you have this big atom and the nucleus is way on the inside and on the outside is the electrons, well, if this atom is going to bump into or interact with another atom, it's the stuff on the outside that would be doing that interacting. So it will specifically be the electrons that are interacting with each other, 2 electrons from different separate atoms, and that again determines the chemical behavior of the atom. So if we want to know the chemical behavior of the atom, we need to know a little bit more about those electrons and where they happen to be located at. And this is what an electron configuration shows us. An electron configuration is really a picture or some type of representation that shows us where those electrons are at, most probably. Okay, again, they are moving all of the time, so we can't pinpoint exactly where they're at, but we can get a good idea of where they happen to be. So if you look at this periodic table snapshot, and we're just showing some of the elements on this particular periodic table, we see these rings located around the nucleus. And these rings are showing us electrons sitting in them. Okay, so that would be my electron for hydrogen. And we're seeing where those electrons are at. If we look down here at lithium, you can see that lithium, the electrons for lithium, we've got some that are a little closer, and then we have some that are a little bit further out. all of these different elements that you see on this table, we're seeing, again, where those electrons are at. Some of them happen to have electrons only on the first level. Some of them have them also in the second level or the second ring. Some of them have them even in a third ring. And really, as our atoms get bigger and bigger, we'll see more and more levels or rings wrapped around that nucleus, which in this case is just being shown as the gray dot in the middle. So that's the nucleus. That would represent protons and the neutrons. We're just not showing all of the detail of that in this particular picture. So if we were to look at, what's going to happen, why is this atom going to interact with some other atom? Well, the reason for atoms interacting with each other is that the unpaired electrons, or in other words, the electrons that are sitting there all lonely in their picture, they would like to have a partner beside them. That's the way that I like to describe it. So if we look at carbon, notice that carbon's got an electron right here that's all by itself. This electron is all by itself. This electron's all by itself, and so is this one over here. And those are the unpaired electrons that we're referring to. Those unpaired electrons would really like to have a partner right next to them. And so if an atom can get a partner next to all of the unpaired or lonely electrons, then that will make a very stable atom. If we look at this column over here, all of those elements don't have any unpaired lonely electrons. So those atoms happen to be perfectly stable on their own, and we don't see them interacting with other atoms. We don't see them forming bonds with other atoms. They are all by themselves. If we look at the columns, if we look right here, if we look at carbon and then silicon below it, both of those have 4 electrons that are lonely, or 4 electrons that are unpaired. So those will tend to interact with other atoms so that they can get a partner for each one of those 4. This column would like to get partners for 3. So nitrogen and phosphorus, they will behave very similar to each other because, again, each one has 3 that they need to find a partner for. Okay, so stable atoms will manage to obtain a full ring on the outside, and that full ring is going to have a partner for everybody. The second shell, the second ring, this one fills up with 8 electrons. So if carbon was to obtain a partner for each of its 4 electrons that it has, it would have 8 total in that shell. That would make it stable. Nitrogen would need to get 3 more because it already has 8. The third shell is also going to fill up with 8 electrons, and all of those elements that are found in the third shell, they are trying to obtain partners for those unpaired or lonely electrons that they have in their shell.